We've done the derivatives in a fair amount of depth, but I want to go a little further with each of them and just discuss their graphical significance. What does a positive first derivative mean graphically? How would you sketch the second derivative being negative? Being on top of all of that gives a depth of understanding of the derivatives that will prove so useful to you down the track. So it's important to get your head around this. I'll go through each of them individually and just express the graphical significance. So our three functions we're going to work with are the f of x, which is the original curve, and what the f of x tells you is it tells you the value of the curve, whereas f dash x, which is the first derivative, tells us the gradient of the curve, and the f double dash x, which is the second derivative, tells us the concavity of the curve. Let's explore each of those a little further. Firstly, the f of x. So here's a graph. What I want to do is I want to show you where f of x is greater than 0. In other words, as we said there, the key word is value. So where is the value of the curve greater than 0? Well, it's going to be anywhere that's above the x-axis. So in this curve specifically, it's going to be those parts there. That is where f of x is greater than 0. Therefore, where's f of x less than 0? Well, that's just where it's below the x-axis. That's where the value, keyword, is less than 0, or where the value is negative. So it's these lines there. And finally, where's f of x equal to 0? So where's the value of the curve equal to 0? Well, simply where it's on the x-axis. So it's going to be these 3 points over there. And those 3 points are what we call the x-intercepts, or the roots. So the important point to take out of it is if you let f of x equal 0, you'll find the roots, or the x-intercepts. Bang. Okay, let's do f dash x, first derivative. So there are 3 equations again. Now we're just going to focus on our f dash x, which is key thing, it's our gradient. You can use f dash x interchangeably with gradient. So there's a curve again. Now we want to know where's f dash x greater than 0. In other words, where's the gradient greater than 0 on that curve? So where is the gradient positive on that curve? Well, we know that positive gradients are like the tick. So it's going to be here and here. That's where there's a positive gradient in the curve. What about where's f dash x less than 0? In other words, where is the gradient less than 0? Well, it's going to be where it's sloping down. It's where there's a negative gradient, which is just there. And the final one, where's f dash x equal to 0? That is where there's a horizontal gradient, where it's a flat gradient, as you can see by those 2 lines there. So it's on those 2 points. And that's really key. We've discussed that our turning and stationary points. So to find them, you let f dash x equal 0. But you can now see it graphically why that's important. So you can find your stationary points by letting f dash x equal 0. We did that in previous lessons, but that is going to become bigger and bigger throughout this whole course. Okay, our second derivative, our f double dash x. So remember that you can use interchangeably as the concavity. So think of it as the concavity. So we take that same graph and we want to know where is f double dash x, or where is the concavity greater than 0. Remember we used the little analogy. The f double dash x is like your mood. Where your mood is positive, you are happy. Where you're happy, you're concaving up because you're smiling. When your mood is negative, you're sad, which is concaving down. So, where's the concavity greater than 0? So where's it concaving up? Well, you should be able to look at that and see it's that part there. And f double dash x is less than 0. So in other words, where is it concaving down, or where is it sad? Because if your mood's negative, you're sad, concaves down. Just that part there. And finally, what happens in between? Well, that's when f double dash of x equals 0. It's a change in concavity. That is the one point where it goes from negative to positive, the concavity, or positive to negative. That is the change in concavity, where it goes from happy to sad. And that specific point where it changes, often it's quite subtle, but that specific point is known as our point of inflection, or our POI, which we discussed last time. So to find those POIs, you need to let f double dash x equal 0. But don't forget to test it, which we'll touch on again, but it's important that you just confirm that the concavity changes through a manual test. Annoying, frustrating, but got to get it done. So let's quickly summarize again what each of the derivatives do. Your original, the f of x, is your value. Your f dash x is your gradient. Your f double dash x, your concavity. Now, with your value, with your f of x, you find the roots. So the most important thing to take out of that is you find your roots when f of x equals 0. So it's important for finding your roots. Your f dash x, you find your stationary points when you let that, the f dash x, equals 0. And you can find the POI, the points of inflection, when f double dash x equals 0. Although that one you actually do have to test to make sure. You have to do the manual test. But you look across there, when you let f of x equal 0, you find your roots. When you let f dash x equal 0, you find your stationary points. When you let f double dash x equal 0, you find your POIs. So each of them have the important functions. One other function that I've left out there, f double dash x, could also be used to determine the nature of the stationary points that you found. And the way that you do that is you sub in your x value of the stationary point into f double dash x to determine its nature.